A one-dimensional array is like a row of lockers. Each locker has a number the index and can hold a single value of the same type. The purpose is to store a fixed size collection of homogeneous items so that we can reach any item directly by its position. C. int scores 10 declares an array named scores that can hold 10 integers, indexed from 0 to 9. C++, same syntax as C, but we can also use std array of int 10 scores for a fixed size container with added safety. Java int brackets scores equals new int 10. The type comes first in brackets and the new keyword actually creates the storage. In all three languages, the element type int, double, char, etc. must be the same for the whole array. Static allocation means the compiler decides the size and location of the array before the program starts running. In C and C++, int of 5 inside a function typically lives on the stack. The memory is contiguous and released automatically when the function returns. In Java, every array is allocated on the heap, but the reference variable, for example int array a, may be on the stack. Dynamic allocation lets the program decide the size at runtime, using new in C++ or Java, or malloc or calloc in C. The resulting memory block is also contiguous, which makes pointer arithmetic simple. The address of an index I equals base address plus I times size of element. This contiguity is why we can iterate with a single loop, and why cache lines are efficiently used. 3 common ways to give an array its initial values. Inline compile time initialization, values are written directly in the source code. Example C/C+:, int of 5 equals open brace 1, 2, 3, 4, 5 close brace. Java int open bracket close bracket a equals open brace 1, 2, 3, 4, 5 close brace. The compiler copies these constants into the array when it is created. Loop-based runtime initialization. A for loop assigns each element, useful when the values depend on calculations or input. Example C++ for open parenthesis int I equals 0 semicolon I less than n semicolon I plus close parenthesis a open bracket I close bracket equals I times I. Default values. If you allocate an array without explicitly assigning each cell, the language fills it with a default. See local arrays indeterminate garbage values. You must set them yourself. See static global and C++ new /Java zeros for numeric types, false for booleans, null for object references, \0 for chars. Remember, the default rule is a safety net. Relying on it for logic can cause bugs, especially in C where uninitialized locals are undefined behavior. Array indexing starts at 0 in C, C++, and Java. The expression I means go to the ith slot from the start of the array. Bounds checking is the act of verifying that 0 less than or equal to I less than length. In C/C++, the language does no automatic bounds checking. Accessing a -1 or a length reads or writes memory that does not belong to the array, leading to undefined behavior often crashes or subtle bugs. In Java, the runtime always checks bounds and throws array index out of bounds exception if the index is illegal, making the error easier to catch. Off by 1 errors happen when the loop runs one step too many or too few. Example, to some n elements a common mistake is for I equals 0, I less than or equal to n, I increment sum plus equals a I, the less than or equal to includes a n which is out of range. The correct condition is I less than n. Visual analogies. Counting locker numbers 0 to 9 but mistakenly counting 0 to 10, you try to open a non-existent locker. Tip: always write the loop condition in the form I less than size, and keep the size in a variable int n equals size of a divided by size of a 0 in C/C++, a dot length in Java. Because a one-dimensional array is a contiguous block of memory, its operations have predictable costs. Access a sub I is O one time. The computer computes the address by a single arithmetic operation and reads/writes the memory cell. Update a sub I equals value also O1 for the same reason. Search a linear scan for I equals 0, I less than n, I plus if a sub I equals key costs O n time in the worst case because each element may need to be examined. If the array is sorted binary, search reduces it to O log n, but it still requires random access which the array provides. Insertion deletion: if we keep the array tightly packed, inserting at the beginning or middle requires shifting up to n elements, costing O n. Deleting similarly requires shifting. Space the array uses n times size of element bytes plus a tiny constant overhead for the length field in Java or for the pointer reference in C, C++. No extra per element pointers unlike linked structures. Thus arrays excel when you need fast random access and know the size in advance, but they are costly for frequent mid-array insertions or deletions. Prefix sums, suppose we have an array a sub 0 to n-1. Define pref 0 equals a 0 and pref I equals pref I-1 plus a I for I greater than 0. Then the sum of any subarray L, R is pref R minus pref L-1 if L is greater than 0 otherwise 0. This turns a O of R minus L query into O of 1 after an O of n preprocessing. Mathematically, sum of L, R equals the sum over k from L to R of a sub k equals P sub R minus P sub L minus 1, where P sub I equals the sum over k from 0 to I of a sub k. Frequency counting. When the values lie in a small known range, for example 0 to 100, we allocate an auxiliary array freq of size 101 initialized to 0. For each input value x, we increment freq of x after processing freq of v holds how many times v appeared. This is the core of counting, sort, and histogram building. Sliding window. To compute the sum of every window of size k, we first compute the sum of the first k elements, then slide. The window sum becomes window sum minus a sub I minus k plus a sub I. The array lets us access the element leaving and entering the window in O of 1. These patterns appear in competitive programming, data analysis tasks, and everyday problems like total sales of the last 7 days or how many students got each grade. Typical exam-style tasks that test mastery of one-dimensional arrays. Reverse an array, swap symmetric elements. For I equals 0, I less than n divided by 2, I increment. Swap O of I and O of n minus 1 minus I. This runs in O of n time and O of 1 extra space. Find maximum or minimum. Initialize max equals of 0 or integer max and loop for I equals 1, I less than n, I increment. If O of I greater than max, then max equals O of I. Same for minimum. O of n time, O of 1 space. Compute sum or product, accumulate sum plus equals of I and prod times equals of I while iterating. Beware of overflow for product, use long or modular arithmetic. Linear search, return the index of the first occurrence of a target value. For I equals 0, I less than n, I increment. If O of I equals target, then return I. If not found, return -1. Complexity O of n. Count occurrences, combine linear search with a counter. Count equals 0, for I equals 0, I less than n, I increment. If O of I equals target, then count ++. Check for palindrome, compare symmetric elements. Boolean OK equals true, for I equals 0, I less than n divided by 2 and OK, I increment. If O of I not equal to O of n minus 1 minus I, then OK equals false. In exam answers, always show the loop bounds correctly I less than n, not I less than or equal to n, and explain the time and space complexity. Sample code in C++ for reversing. Void reverse array takes integer array and an integer n open brace for integer I equals 0. I less than n divided by 2. Increment I, open brace integer temp equals O of I. O of I equals O of n minus 1 minus I. O of n minus 1 minus I equals temp, close brace, close brace. Explanation: when solving a problem, you must pick the right container. One-dimensional arrays give you O of 1 random access and minimal memory overhead, but their size is fixed after allocation unless you allocate dynamically again, and inserting deleting in the middle is costly. Vector C++ std vector Java ArrayList are built on top of arrays but manage size for you. They grow automatically, usually by doubling capacity, so you get amortized O of 1 pushback/add and still O of 1 random access. The extra capacity uses a bit more memory and occasional reallocation, copies all elements O of n spike. Linked lists store each element in a separate node with a pointer to the next and possibly previous. They excel at O of 1 insertion or deletion at any position if you already have a pointer to that node, but they lack O of 1 random access to get the ith element. You must walk I steps O of I. They also use extra memory per node, the pointer, and cause poor cache performance because nodes are scattered in memory. When to choose arrays? The problem states a maximum size, for example 1,000 students, and you need fast indexing. You will perform many reads and only a few endappends. When to choose vectors? You do not know the final size in advance, or the size grows while reading input. You need both fast random access and occasional appends. When to choose linked lists? The task involves many insertions deletions in the middle, and you already have iterators or pointers to those positions, for example implementing a queue where you only pop from front and push to back, though a deck is often better. Understanding these trade-offs helps you decide which structure makes the algorithm simpler and more efficient.